Hi there. Welcome back to another video describing the idun cartridge for the Commodore 128. In this video I want to talk about the VDC and specifically the creation of VDC modes and an API for accessing those modes that are part of the idun cartridge software. Original motivation for this was I wanted to be able to write new software for the Commodore 128 that took advantage of the VDC and its many graphical capabilities, some of which are not all that well known or all that well documented, especially in comparison to the VIC-2, which has been kind of well studied, well documented over the years. But the VDC has a lot of capabilities, and in order to access those, you need to be able to set up the chip in some kind of sensible manner and know that you can recreate that setup and then it will work on machines of various specifications and monitors of various specifications. So what do I really mean when I talk about a VDC mode? What is that? Well, the VDC chip has 37 programmable registers. And these registers affect virtually everything about the video display. It affects the pixel resolution, the color resolution, how many color cells are being displayed, and the size of those color cells, the positioning of the frame on the monitor, the horizontal and vertical sync timings related to that, the horizontal and vertical frequencies, whether or not you have progressive or interlaced scanning, and even the video RAM configuration and timing is affected by these registers. And so these registers are confusing to work with, and there's really no safeguards. So many setups, many values that you could stick in these registers are just not viable. Or if they are viable, they're only viable with certain monitors that would support those timings that you're going to output. So what I want to do was kind of define some modes that are realistic and that cover a pretty wide gamut, so that, you know, given an application that you have in mind, you can select the mode that's most appropriate for that application, easily set it up through an API, and then just draw graphics on the screen. That was the idea. So these are the VDC modes that I came up with. This is an overview of them. There's 8 modes, where mode 0 is just the 80-column text mode. So that's easy. We're all familiar with that. And then modes 1 through 7 are for various monochrome and color graphics setups, and also various memory configurations too. So starting with mode 0, because that's the easiest to understand. We're all familiar with that. Really the only thing that you would want to adjust with mode 0 is the number of rows of text that is displayed. So the VDC can display around 30 rows of text in progressive scan and up to around 50 rows in interlace mode. So just as a quick introduction to mode 0 and the mode command, let's do a couple things in the idun shell. So if I just type mode, then it will tell me that the VDC is currently active and it's set for 80 columns by 27 rows. If I want to change that, I can do a command like mode VDC 0, so mode 0, and let's change it to 80 columns by 25 rows. And now you see it says VDC 80 by 25 active. We could increase it to mode VDC 0 80 by 29. So now we have a nice long 29 row display. And another thing you can do with the mode command related to mode 0 is set the character set, the downloadable character set that the VDC has loaded in its memory and will use for displaying characters. So if I do mode character set browse, that'll load this specific character set into the VDC's memory, and you'll see the text changes. So by way of brief overview to the graphics modes 1 through 7, first you should understand that modes 1, 3, and 5, what I call the medium and low resolution modes, these all require only the standard 16 kilobytes of video RAM. They're all non-interlaced, as opposed to modes 2, 4, 6, and 7, all of which require 64K of video RAM, and all of which are drawn in interlaced mode. So 1, 3, and 5 is the lower resolutions. 2, 4, 6, and 7 are the higher resolutions. All the way up to mode 7 is what I call super res, 800 by 600 pixels. Also, mode 5 and mode 6 are the ones with the largest number of color cells of these respective categories. So mode 5 you can think of as being near to the CGA, composite CGA 16 color or Tandy graphics quality. And then mode 6 you can think of as being near to IBM EGA quality. And this image that I previously shown is actually rendered using mode 6. So 640 by 480 interlaced graphics mode. So taking a look at the 7 graphics modes in more detail, here we see them listed with their respective pixel resolution and color cell resolution. And let's begin by taking a look at mode 1 and mode 2, the monochrome modes. So using the mode command again, we can test each mode, see what they look like by using mode debug. In this case, VDC 1. So we want to see what VDC mode 1 looks like. So this is the normal kind of standard 640 by 200 monochrome display that most people have seen before from the VDC. It's sort of a stock mode. If you change the minimal number of register settings in the VDC, this is the mode that you can get. So as I say, it's monochrome. You can have any of the 16 colors as long as you only have one of them. Non-interlaced and useful for some things. For example, the default screensaver in idun, a program called Liner, uses mode 1 and uses mode 1 to draw these lines on the screen that sputter about and change colors as they bounce off the borders. And one thing you'll notice about this is, well, it's not impressively fast. And this gets to one of the main limitations about the VDC is how you can access the video RAM. The VDC, like I said, it has 37 registers, but there's only 2 memory addresses that are accessible, D600, D601. And through just those 2 memory addresses, you gain access to all 37 of the VDC's internal registers, plus all of up to 64K of the video RAM. So it's a protocol you have to use, and it's quite slow to do things like this program is doing, which is basically plots random pixels anywhere on the screen. That's kind of the slowest mode of operation that you have to deal with. There are tricks to do things faster. The VDC has hardware support for copy and fill, which is very fast. It also has hardware scrolling, and it also has modes where you can set consecutive memory addresses much more quickly than you can set just random addresses. So for example, if you happen to be drawing a horizontal line, it can do that pretty fast because it's consecutive memory addresses. It's basically a one-line fill. But when you're drawing diagonal lines like this, no, you can only go so fast because of the limitations of the way the memory is accessed. As another example, we'll look at a mouse test. So the idun software supports a 1351 mouse, and mouse test just basically lets you move the mouse around the screen, but you can also click and drag. And if I do that, you'll see that it draws a filled area and draws it really fast. I mean, basically real time. So this is an example of what the VDC can do when you use the built-in copy and fill capabilities. So that's mode 1. So if you're lucky enough to have 64K of video RAM in your Commodore 128, then you can also use mode 2. So we can do mode debug VDC 2 to see what that looks like. And this is a much higher resolution, twice as many pixels version of mode 1. So it's 640 by 480, again, monochrome. And this can actually be used to display lots of old, like classic Mac pixel art. If it's converted to a format that the idun software understands, which in this case is going to be the PBM monochrome graphics format, then you can display those images. Basically, the software detects what the resolution is of the image and then selects an appropriate mode, usually going to be mode 2. So if we just open the browser, I can show you some of those images. And we'll just change directory into idun base and pix and mono. And you'll see there's all kinds of PBM files in this directory. So we use the show VDC command. And let's just do amiga.pbm, f16a.pbm, and ferrari.pbm. And so each of those will be displayed in turn. You just press any key to advance to the next picture. So high resolution monochrome images. So you will have noticed that mode 1 and mode 2 are kind of related, and that mode 2 is the higher resolution version of mode 1, requires 64K. Mode 1 works with 16K of video RAM. Similar for mode 3 and mode 4. These are both color modes. Mode 4 is the higher resolution version of mode 3, requires 64K of video RAM. And these both are distinct in that they have pretty fat color cells. So the color cells are 8 by 8 pixels, giving you 40 by 32 color cells in the low res mode 3 and 80 by 60 color cells in the higher res mode 4. So let's take a look at mode 3 first of all. So this is 320 by 256, up to 320 by 256 I should say. So we'll do mode debug VDC 3. And you'll see it very quickly puts up this color bar display. And it is quick because it's using the hardware fill capability of the VDC. And it is colorful. And you can do a lot with this particular mode. I really like mode 3. I think it offers a good balance. So for example, mode 3 is compatible with images made for the ZX Spectrum computer. So if we go back into the browser and we'll go up into the Spectrum directory, see there's a ton of images in here. We'll just do a directory showing all the different image files ending in .scr. So these are ZX Spectrum image files. And we have a show ZX command. So we'll do show ZX and we'll just do batman.scr and we'll do breath.scr. And so here's the Batman image. As you can see, it looks pretty good, mostly because a good artist did some pixel art tweaking to make it look good, because it's not high resolution, and it's certainly not high in terms of the color cell support, with only 40 color cells across the screen and maximum of 32 vertically. But it doesn't look too bad. Same thing again with this image. Great use of the palette. And I think it's really neat that you can just directly transport these images over from the ZX Spectrum and display them on the VDC. So another thing that's neat about mode 3 is it only requires 16K, but if you have 64K, then you can enable double buffering. So there's an API in the idun software for doing double buffering, and basically it just sets up a second memory area in the video RAM for a second screen. And of course you can toggle between the two screens very quickly, so you can get smoother redraws or do things between the two images like fades. Change to the E drive and we'll run cube.app. So this little demo uses mode 3 and uses the double buffering. And as you can see, it's only managing a couple frames per second. That's not because the calculation is slow. The actual program is written in Lua, so computing the vertices for the cube is actually super fast. But the drawing that the VDC has to do, again, it's these diagonal lines. It can only do it so fast. But with the double buffering, at least you get a smooth transition between the frames. So that's another use for mode 3. So then mode 4 is our higher resolution version of mode 3. And we can do mode debug VDC 4. And you'll see you get the same color bar display like we showed before, but this time 640 by 480 resolution. So actually 4 times the number of pixels is mode 3 and 4 times the number of color cells. Practical uses for this mode, kind of not yet determined. Obviously you could do something like those ZX Spectrum images, but at 4 times the resolution, so that might be neat. But other uses are there to be explored for mode 4. Next we'll take a look at mode 5 and mode 6. So once again, mode 5 and 6 are related. Mode 5 is the lower resolution version that will work with 16K of video RAM, and mode 6 is the higher resolution one requiring 64K. We'll first look at mode 5. So we're going to do mode debug VDC 5 this time. And so compared to mode 3, mode 5 has much less chunky color cells. It's 40 by 100 color cells. They're 8 by 2 pixels in size compared to the maximum 40 by 32 color cells with mode 3. So you can use dithering. You can get more shades through dithering the colors together, kind of like this debug screen displays. And if we want to take a look at some color images, there are 2 in this directory that are compatible with mode 5. So we'll do show VDC, aegis.vdc, and c64.vdc. So this is actually a conversion from a Amiga IFF file, low-res Amiga file. This has not been tweaked by hand at all. This is just the conversion that was done in an automated fashion. So it's not great. You can see there are obvious places where the pixels could be touched up if you did manual editing with a paint program. But it does show the the range of colors that you can at least simulate using dithering. And likewise, this is also an Amiga IFF image that was automatically converted to a mode 5 format. And again, shows you can get pretty substantial color range, even though it's low resolution. Just because those color cells are so much smaller, you get better quality image. And again, this one could be tweaked, touched up to get rid of some of the artifacts in it from the conversion. Just like mode 3 can be used with double buffering. There's enough memory. If you have 64K, you can have multiple screens in memory. And then mode 6 is the higher resolution version of mode 5. So let's do mode debug VDC 6, and you'll see you get a similar display, but with clearly higher resolution and kind of a more convincing use of the dithering to create different shades. This shows presumably 56 different shades you can create through dithering. And if we use the show VDC command again, let's do idun and Terminator and Loch Ness. So these are all mode 6 images. You can see they take a little bit longer to load. They're actually quite sizable. They fill most of the 64K of video RAM. So this is another automatically converted file, I think from originally a PNG image. Has not been tweaked or touched up manually, but provides a pretty decent image quality, and you can see a lot of those artifacts could be easily removed by touching it up in a paint program. So this is Terminator, and this actually you may have seen before because it's part of the VDC Mode Mania demo, and actually several of the images used in that demo are compatible with VDC Mode 6. So I converted those images over to the VDC Mode 6 format for display using Show VDC. And here you see an example of what you can do with Mode 6 if you do actually tweak the image and clean up any artifacts from converting it from its original format. So this image I think looks pretty good, and that's why I say EGA quality images are possible with the VDC. And another one here, this also comes from the VDC Mode Mania demo slackness. Again, almost has like a pastel color characteristic to it with the dithering and with the image having been touched up by hand. Looks really pretty good. So that brings us to the final VDC graphics mode, Mode 7, which I call Super Res, which allows images of 800 by 600 resolution with 64K of video RAM, and it uses just about all of that memory. So there's one image I can display for Mode 7. It's this Lion 64K. We'll do Show VDC Lion. And you see you get this large monochrome image. Another thing you can do with the Show VDC command using the number keys is you can change the color that's used for drawing the image. So I kind of like this color. You can see quite a lot of pixels. One thing you don't get, because I'm showing you this in the emulator, is that when you run Mode 7 on a CRT, it fully occupies edge to edge the display of the CRT. In fact, most monitors, it won't really fit all 800 by 600 pixels. You'll have some overflow to the off-screen area. So it uses full use of the overscan area to display this image. And that covers all 7 of the VDC graphics modes. So I hope you found this informative. If you want to learn more, certainly take a look at the GitHub page linked below for the idun-cartridge project. There you can find source code for commands such as mode and show VDC and show ZX. And you'll see there's an API there that's actually pretty easy to use. You just pick the mode you want that's most appropriate for your application and quickly set that mode, so you don't have to worry about the VDC registers. Once your mode is set, you can use a simple API to draw pixels onto the screen, not having to worry about what specific memory address within the VDC is being used for those pixels, not having to worry about whether the screen is progressive scan or interlace scan, and just makes everything pretty easy. So thanks again for watching.